Hi everyone, my name is Junwei Su, a PhD student from the University of Hong Kong. Today I'm presenting the paper on the topology awareness and generalization performance of graph neural network. So let's start with the why question. Why should we care? Many computer vision problems and machine learning problems can be laterally modeled as a graph learning problem. And graph neural network, abbreviated as GNN, is the state of a family of neural networks for learning graph structured data. A defining characteristic of GNN is their use of a spatial approach through message passing on the graph structure for feature aggregation. This is captured by the figures on the right-hand side. This process enables GNNs to preserve structural information or dependence from the underlying graph structure, and we refer to this ability of GNN as its topology awareness, allowing them to be highly effective in graph-related problems. Because of its empirical success, there is an increasing attention from the community to study the theoretical property of GNNs. One common framework used is to study the so-called expressive power of GNN, which is defined to be the ability to differentiate different graph structures. However, it remains unclear how topology awareness of GNN connect with the generalization performance. Therefore, our goal in this paper is to bridge the existing gap. Our main contributions are twofold. First, we provide a novel theoretical framework to study the relation between the topology awareness of GNN and their generalization. Second, we present a case study based on the shortest path structure to validate our framework and showcase its application potential. Please refer to the paper for the case study. So for the framework, there are two main components. The first components relate to the similarity measures. Given a structure of interest, we assume there exists a distance function measuring the structural similarity of two groups of vertex. The second component is a dot from the approximate embedding. It's called distortion, capturing the relation of two distant functions. The formal definition of the distortion is given on the right-hand side of the slide. Intuitively, the distortion score alpha captures the nonlinear change in similarity between two spaces under a given mapping. In our case, the mapping is a GNN. Then, for a given structure, we say a GNN is highly aware of that structure if the distortion is close to 1. So under the proposed framework, our first main result characterizes the relation between the topology awareness of GNN and its generalization. It states that the generalization of GNN with respect to a given structural measure is determined by 1. The training error of the training set, 2. The structural similarity between the test set and the training set, and 3. The distortion, in other words, how aware GNN is toward a given structure. These results establish a framework and a connection between the topology awareness of GNN and its generalization for a given structure of interest. Our second main result further extends the first main result and uses the framework to compare the generalization between two different test groups. It states that for two test groups of the same size, if the structural similarity of group 1 toward the training set is higher than group 2 with respect to some threshold dependent on the distortion, then GNN is going to perform better on the group 1 than group 2. This result provides a framework to infer how a given GNN is going to perform for different test groups. This is also referred to as the subgroup generalization in the literature, and it has interesting implications in other important uses of GNNs, such as fairness and training set selection. To conclude, in this paper, we propose a novel framework for connecting the topology awareness of GNN and its generalization based on the concept of distortion. As such, we have bridged the existing gap in understanding GNN. For the limitation, our study so far primarily examined the translative setting.
Expanding this analysis to the inductive setting can offer a more comprehensive view of generalization capability. In addition, it would be interesting to see more application of our framework and results in more severe application where topology is important for the underlying problem structure. Thank you for the attention.